Imagine a heavy-duty autonomous drone hovering near the edge of a jagged cliff.
Oh, wow. Okay, setting the scene.
Right. And the wind is just howling. It's completely unpredictable, gusting from, I don't know, a dozen different directions, just slamming into the side of the drone.
Yeah, which, by all basic laws of physical intuition, should mean that machine gets thrown against the rocks.
Exactly. I mean, it has no eyes, it has no pilot moving a joystick, yet it stays perfectly locked in place.
Fighting back against those invisible forces.
With flawless precision. And what's keeping it in the air isn't just, battery power or spinning propellers. It's a computer desperately performing high-speed calculus every single millisecond.
It's wild to think about. And that unseen mathematical engine, it's constantly running in the background of almost everything we rely on.
Yeah.
I mean, we tend to view calculus as this hurdle designed to punish engineering students.
Oh, definitely. A lot of bad memories for people, I'm sure.
Right. But it is actually the hidden connective tissue of the modern world.
Which brings us perfectly to the focus of today's deep dive. We're exploring a really fascinating, highly specific set of source notes today.
Yeah, these are great.
They're titled Day 22 Calculus, Theory, Engineering, Code. And these materials pull heavily from fundamental texts, specifically Insert Chapter 7, Sections 7.7 and 7.8.
Very foundational stuff.
Right, and our mission for you today is to pull these concepts out of the textbook and into the physical world. We're going to unpack how intimidating concepts like, definite integrals and the fundamental theorem of calculus actually function as the literal blueprint for rockets, electronics, and, well, those autonomous drones.
Yeah, and what makes this particular source material so compelling is that it forces us to cross domains.
Yeah.
It doesn't let you just memorize a formula and move on.
Right, no rote memorization here.
Exactly. It demands that you trace the theoretical math directly into a physical engineering lab and then map it all the way into the digital software code that, brings those machines to life.
Okay, let's unpack this by starting with the theoretical fuel that powers the whole system. The source material begins with a very traditional, very dense definition of a definite integral.
Oh boy, the textbook definition.
Yeah, brace yourself. It states that it, quote, calculates the exact accumulated sum of a quantity over a specified interval, geometrically representing the net signed area under a curve.
Rolls right off the tongue.
Right. I mean, I have to push back on that kind of framing. For anyone listening who doesn't spend their weekends doing advanced algebra, phrases like accumulated sums and net signed area, they just feel like a wall of jargon.
They absolutely do. It's
Yeah.
a definition that is, well, mathematically flawless, sure,
Yeah.
but intuitively, it's completely opaque.
Yeah. So let's try to visualize it differently. Imagine you're tasked with perfectly icing a cake.
Okay, I like cake.
Good. But this isn't a standard flat sheet cake. It's a chaotic, wildly asymmetrical, like Dr. Seuss-looking creation.
Oh, I see where you're going.
Right. It slopes up, it dips sharply in the middle, and the far side just towers over everything else. The height is constantly varying. If I ask you exactly how much icing we need to cover the entire side of that cake, you can't just multiply length times height.
No, you can't. There's no simple geometric formula for chaos.
Exactly.
Because every single millimeter you move along the base, your requirement changes.
So you use a mental trick. You imagine slicing that cake into infinitely thin, microscopic vertical slices. Slices so unbelievably thin that for each individual slice, the top is basically flat.
Right. You're zooming way, way in.
Yeah, you figure out the tiny speck of icing needed for one microscopic slice, and then you add up the millions of tiny slices across the entire length of the cake to get your exact total. And that is what a definite integral is doing.
I love that analogy.
It takes a continuously shifting reality, slices it into infinitely thin pieces, and adds them up to find the total accumulation.
That paints a much clearer picture. You're taking a changing rate, whether that's the bizarre height of a cake, the fluctuating speed of a car, or the flow of water, and you're finding a way to measure its total accumulated footprint between a starting line and a finish line.
And those lines are your boundaries.
Exactly. Those are the boundaries.
But actually doing that math manually, calculating infinite microscopic slices and adding them together, I mean, that sounds entirely impossible.
Oh, it was. For centuries, it was a massive stumbling block. Mathematicians were relying on incredibly tedious geometric approximations to figure this out.
Wow.
But what's fascinating here is the introduction of the Fundamental Theorem of Calculus, or the FTC. The source notes highlight this as the ultimate bridge.
The ultimate bridge.
Yeah, it's the theorem that links differential calculus, which is, this study of instantaneous rates of change with integral calculus, which is the study of total accumulation.
The sources actually split the FTC into two parts. Let's walk through the mechanics of both.
Sure. So the first FTC establishes a profound relationship. It proves that integration and differentiation are inverse operations.
Meaning what, exactly?
They're structural opposites, just like multiplication undoes division. If you figure out the exact rate at which your cake's height is changing, and then you integrate that rate of change, you get right back to the original accumulated shape of the cake.
It's like the universe giving us a mathematical undo button.
Exactly. It's deeply elegant. But the second FTC is where the practical application just explodes. This is the shortcut that saves you from having to manually calculate infinite slices.
Thank goodness for shortcuts.
Right. The second FTC states that if you know the antiderivative of your curve, you can evaluate that wildly complex definite integral just by looking at your boundaries.
Okay, stop there for a second because we definitely need to clear up the word antiderivative.
Fair enough.
For someone without a math degree, that just sounds like the opposite of a derivative, which doesn't really help us visualize anything.
That's a fair point. Let's ground it. Think of the derivative as your daily bank transactions. You spend $3 here, you deposit $50 there. It's the instant daily rate of change in your wallet.
Oh, okay, follow that.
The antiderivative is the grand total balance of your bank account at any given moment.
Right.
It's the master blueprint that tracks the overall accumulation resulting from all those tiny daily changes.
So the second FTC says that if I have that master blueprint, that grand total tracking function, I don't have to add up all the infinite microscopic changes between point A and point B.
You don't have to look at the microscopic journey at all. You just take the total state of things at the very end, point B, and subtract the total state of things at the very beginning, point A.
Oh, wow.
Yeah, the formula that source provides is f of B minus f of A. If you want to know how much money you saved over a year, you don't need to add up 365 days of coffee purchases and paychecks.
Right, that would take forever.
Exactly. You just look at your bank balance on December 31st and subtract your balance from January 1st. The difference is your total accumulation.
That is a massive conceptual leap. You bypass the infinite slicing entirely.
Completely.
So we have this theoretical shortcut, this end state minus beginning state formula that gives us perfect total accumulation. Let's take this out of the theoretical banking and baking classes and put it into physical engineering.
Let's do it.
The source notes pivot directly into aerospace. Let's talk about rocket launches.
Perfect example. Aerospace relies on this extensively because rockets are, well, notoriously nonlinear systems.
See, I used to think a rocket engine just turned on, almost like a car engine or a light switch. You ignite it, and it outputs a flat, constant amount of force until it runs out of gas.
A lot of people think that.
But looking through these notes, especially concerning solid rocket boosters, that assumption is entirely wrong. The force produced by a rocket is a wildly changing curve.
It is entirely chaotic. Inside a solid rocket booster, the propellant isn't just a big, dense log of fuel. It usually has a hollow core down the center, often shaped like a star.
Shaped like a star, really?
Yeah, to control the burn rate. When it ignites, the fire burns outward from that hollow core toward the outer casing.
Which means as the fire burns deeper into the propellant, the physical shape of the burning surface is changing.
Yes. As the hollow core expands, there is literally more surface area of fuel catching fire at any given second.
Wow.
And more burning surface area means more gas being violently expelled out the back, which means more thrust. As the geometry of the solid fuel changes, the thrust curve ramps up, peaks, and eventually drops off as the fuel runs out.
But if that physical pushing force is constantly shifting and varying every fraction of a second, how do aerospace engineers figure out exactly how fast the rocket will be traveling when the engine finally shuts off? I mean, they can't just multiply a constant force by time.
No, they turn to the definite integral to calculate what is called total impulse. They take that shifting, chaotic thrust curve over time, let's call it f of t, and they integrate it over the exact duration of the engine burn.
From time t sub 0 to time t sub 1, like the notes say.
Exactly. From ignition to engine cutoff. That mathematical accumulation of the changing force gives them the exact total change in momentum. And once you have the momentum, calculating the final velocity, which the notes refer to as m times delta v, is trivial.
So they use the mathematical area under that thrust curve to derive a guaranteed physical speed. The physical shape of the fuel dictates the mathematical curve, and the integral of that curve tells you exactly where the rocket is going to end up.
It's brilliant. If they couldn't calculate that definite integral flawlessly, The spacecraft would miss its intended orbit by miles.
That's terrifying.
Yeah. And what the sources highlight next is the profound symmetry of the universe. We can take that exact same mathematical logic, scale it down from a multi-ton rocket, and apply it to the microscopic electronics inside your smartphone.
Right. The second domain? We're talking about electronics, capacitors specifically. They're those tiny little cylindrical components sitting on almost every green circuit board ever manufactured.
They operate under the exact same foundational logic of accumulation. A capacitor is essentially a microscopic storage tank for electrical energy. An electric current, well, that's the rate at which electricity is flowing through the wires.
Okay, so think of a capacitor like a heavy-duty rubber water balloon attached to a garden hose. The water pressure building up inside the balloon is your voltage. The water flowing out of the hose is your current.
That works perfectly.
But in complex electronics, the hose isn't turned on to a steady, constant stream. It's sputtering. The flow of water is fluctuating wildly based on whatever the rest of the microchip is doing at that moment.
Right. That sputtering flow is an alternating waveform. So if an electrical engineer needs to know the exact electrical pressure, the voltage, which we'll call V of t, stretching the walls of that microscopic balloon at any given fraction of a second, simple multiplication is completely useless. The rate of flow is continuously changing.
So they have to integrate the sputtering flow.
They do. They evaluate the definite integral of that fluctuating electrical current from the moment they started observing up to the present instant. They scale that mathematical area by the physical constraints of the capacitor, the 1 over c, from the source text, which is basically how stiff the rubber of your water balloon is.
Got it. And they arrive at the accumulated voltage.
Almost. The sources point out a really critical detail here, the boundary condition. The formula states you have to add v of 0 to your integral.
Oh, right, the initial state.
Exactly. You have to account for any water that was already sitting inside the balloon before you turn the sputtering hose on. You take the initial accumulation, add the integral of the changing rate, and you get your total current reality.
It's crazy how it all connects, whether you're managing fire expanding outward in a solid rocket booster or invisible electrons stretching the limits of a microchip. The definite integral is the universal language of accumulation.
It really is.
But here's where it gets really interesting. Because up to this point, we're establishing that calculus is designed for perfectly smooth, continuous reality.
Right. Smooth curves.
The burning of rocket fuel is continuous. The flow of electricity is continuous. But when I read the third domain in our source notes, computers and software, a massive contradiction jumps out.
Ah, yes. The collision of continuous reality and discrete logic.
Exactly. The physical universe operates continuously, but computers do not. Software operates in rigid clock cycles. A processor chops time into discrete, blocky increments. Tick, tick, tick. Every millisecond, the computer takes a frozen snapshot of the world.
It's entirely disjointed.
So if calculus inherently relies on perfectly smooth, infinitely divisible curves, how on earth does a digital computer, which can only see reality in choppy frames, actually use calculus to fly something like the drone we talked about earlier?
If we connect this to the bigger picture, you are hitting on one of the foundational challenges of modern robotics, translating the smooth physics of the real world into the blocky mathematics of a microchip.
How do they do it?
The sources address this through the mechanism of PID control. This stands for Proportional Integral Derivative Control. It's the algorithmic brain used in almost all industrial automation and avionics.
Okay, let's focus on the I in PID, the integral part. How does that keep our drone from crashing into the cliff face?
Imagine your drone is trying to maintain its hover, but a persistent steady breeze is pushing it slightly to the left. The drone starts to drift. It experiences positional error.
Okay.
If the flight software only looks to the error happening right now, in the current millisecond, it might just think, oh, I'm slightly off center, and apply a tiny weak correction. It doesn't realize it's fighting a relentless wind.
Because it has no memory of the past.
Yeah.
To truly fight back, the software needs context. It needs to know the history of the drift.
Exactly. It needs to accumulate the error.
Mm-hmm.
The drone calculates the definite integral of its positional error over time. The longer it stays drifted to the left, the larger the calculated area of that error becomes. And the software tells the motors to spool up harder and harder to shove the drone back to the right.
But wait, the drone's flight controller is a digital computer. It's getting sensor data maybe 1,000 times a second. It doesn't have a smooth, continuous equation of the wind. It just has a series of isolated data points.
Correct.
So it can't use the perfect f of b minus f of a shortcut because there is no continuous master blueprint function to plug the numbers into.
No, it can't. It has to brute force the math. Since it cannot compute a pure analytical integral, the software dynamically approximates the area under the error curve using something the sources call the trapezoidal rule.
Let's break down how that approximation works under the hood.
Sure. Rather than slicing reality into those practically invisible, infinitely thin slices we used for our theoretical cake, the computer takes the distinct sensor reading from the last millisecond and the distinct reading from the current millisecond.
Okay, two distinct points.
Right. It draws a straight line between those 2 points, creating a tiny trapezoid. It calculates the geometric area of that little blocky trapezoid and adds it to a running tally.
Wow, so it's rapidly summing up discrete, rigid, millisecond-wide blocks of error. It's doing calculus the hard way, adding up the slices manually on the fly because it's trapped in a digital environment.
Yep. And by continually adding up those discrete packet slices, the system builds an approximation of the continuous integral. It forces the system to correct that steady-state wind drift.
You know, this friction between perfect math and digital approximation leads directly to the final section of our source notes. The material insists on a practical exercise labeled 10-minute code.
Ah, yes. The Python script.
Yeah. The instruction is to drop a provided Python script into a file called math_refresh.ipnb. The script is designed to run the pure, continuous mathematical calculation of an integral using the FTC, and then run the exact same problem using the discrete, blocky trapezoidal rule that our drone uses.
A side-by-side comparison.
Right. But why is it so crucial for someone studying this to actually run that code and verify the difference mathematically? Why not just trust the discrete software cycles?
Because reading about the difference between theoretical perfection and algorithmic approximation is, abstract. It's just theory.
Sure.
But seeing the literal numerical gap, the delta between the perfect mathematical reality and the computer's best guess on your own screen, that anchors the concept. When you run that Python script, you see that the digital answer is incredibly close to the true physics, but it is almost never perfectly identical.
Because drawing straight lines between data points creates rigid trapezoids. Those blocky edges don't perfectly capture the graceful curve of continuous reality.
Exactly.
A tiny bit of physical area gets left out, or a tiny bit of non-existent area gets included in the calculation.
And in the real world of engineering, understanding the scale of that tiny error is a matter of life and death. I mean, the difference between a pure integral and the digital approximation might be minuscule over 1 millisecond, but what happens if a system runs for hours or days?
Those tiny errors accumulate. Actually, that makes me think of the infamous Patriot missile software failure in the early 1990s.
That's a perfect example.
Right. The system tracked incoming targets by calculating time in discrete digital cycles. But there was a slight numerical truncation in how the software approximated the time.
A tiny, tiny rounding error.
Exactly. Over a few seconds, it didn't matter. But after the system had been running continuously for 100 hours, those microscopic rounding errors added up. The tracking software drifted entirely out of sync with physical reality, completely missed an incoming missile, and people lost their lives.
It's tragic. And that is the ultimate lesson of the Python script exercise. It teaches you to harness the power of software, but also to mathematically respect its inherent blind spots. Verifying the code forces you to recognize that digital integration is always just a shadow of the continuous physical world.
So what does this all mean when we zoom out? We started this deep dive staring at the intimidating, jargon-heavy definitions of definite integrals and the fundamental theorem of calculus.
Which nobody enjoys looking at.
Right. But we've unpacked how those concepts are the master keys to the engineered universe. They're the logic that allows aerospace engineers to perfectly predict the momentum of a solid rocket motor whose physical geometry is literally burning away.
Yeah.
They dictate the exact electrical pressure building up inside microscopic capacitors. And when our digital systems can't access pure continuity, algorithms like the trapezoidal rule allow our autonomous drones to approximate reality and fight back against chaotic wind currents.
It completely transforms how you perceive the machines operating around you. Once you see the mechanism of accumulation, you realize that calculus isn't just on the chalkboard. It's in the sky, it's in your devices, and it's in the software loops.
But, tracing the difference between the pure mathematics and the digital flight controllers leaves me with a final, slightly unsettling thought from our sources. We learn that to navigate the continuous flowing reality of the physical world, Our discrete digital software has to slice that reality into tiny millisecond packets and draw straight lines between them.
Yeah, it forces continuous physics into rigid digital frames.
Which raises the question of what happens in the microscopic, infinite gaps between those discrete milliseconds.
Oh, wow.
Right. If our computers can only ever approximate the continuous curves of the universe by constantly calculating the area of tiny trapezoids, are our most advanced state-of-the-art digital systems always flying just a fraction of a hair out of sync with true physical reality?
It certainly makes you wonder if a computer ever truly knows exactly where it is.
That is something to chew on the next time you see a drone hovering perfectly still over a cliff face. Thanks for diving deep with us today. Keep questioning the mechanisms behind the machines, keep learning, and we'll catch you on the next deep dive.